Okay. It's too far away. Hello? Oh, okay. Yeah, I think I can't find the. All right. So we have find that a condition that if the periodic function ft is absolutely integrable over a period, then we can construct a trigonometric Fourier series. So let's take an example. Okay, so over. Okay. All right. So because f of x is a periodic function, and so to specify with period to pi, we need only to specify its value within a period to pi. So so we know if x is between minus pi and 0, the value is minus 1. And when x is between 0 and pi, the value is 1. And f can be arbitrarily defined at x equal to 0 and pi. Okay? Because the value of fx pi it is equal to at the minus pi because it's a periodic function. Okay, so we have this one. Okay, and if you draw a figure of this periodic function, and you know that okay, so you see that, and okay, and the value can be arbitrarily assigned at 0 and pi. So so for example, we can put the value here. Okay, and some value here. Okay, so it's a mathematical model of a clock signal. Okay. Right? So now it can be seen that okay, this periodic function is absolutely integrable. The reason is here. So you can see this is so this is 2 pi, and which is finite. So you can see that f of is absolutely integrable things. Okay, so you can see immediately, right? All right, and so we can construct the associated trigonometric Fourier series. Okay, and so before you can see by Euler formulas, A0 1 over 2 pi. Okay, f of x dx. Okay, and you can see, except, so within this period, so within this period, okay, this periodic function, all right, it's an odd function, okay, except if you ignore the point at minus pi and 0, the value at the point x equal to minus pi, 0, and pi, okay, because that for integration you can ignore the value at the discrete points. And so when you look at these parts, you can see it is an odd function. Okay? So it is an odd function. So when we have an odd function, right, the integral is 0 by the asymmetry. Okay. So, okay. All right. And for an, for n greater than or equal to 1, we have right. And now in this interval, cosine function is even function. Right. So this is even function. All right, and this is an odd function. All right. Okay, on this interval. So we just exclude the value of f of x at integral multiple of pi. Okay, so of course, odd function multiplied with even function is also an odd function. So when you integrate an odd function, the integral is 0. Okay. How about Bn? Now you multiply sine function. But sine function is an odd function. So an odd function multiplied with an odd function becomes to an even function. So if it's an even function, then the value may not be equal to 0. So you have to do the integration. Okay. So but you can see because it becomes to be even function. So you can integrate over from 0 to pi. Because the other part from minus pi to 0 you have the same result. Okay. So you have 2 here, and f of x and sine n of x dx here. All right? Because the integrand becomes to an even function. Okay, on the union of these 2 open interval. So okay, and in 0 to pi, f of x equal to 1, right? So this is constant. So you have now. Okay, so this is the definite integral of the sinusoidal function, and you know the antiderivative of sine functions. So you have 2 pi, the antiderivative x minus cosine nx, and here. Okay, so you use the antiderivative to evaluate the definite integral, and so the value x. Okay, so this is 1 minus cosine and pi. And you can see that when n is even, right, the value is 0. But when n is odd, the cosine value is minus 1. So you have 4 and n pi. If n equal to 2k minus 1, when k equal to 1. Okay. All right, so you have this one. Okay, so the trigonometric Fourier series, okay, generated by this periodic function is this one. Okay, from 1 to infinity 4, 2k minus 1 pi, okay, and sine 2k minus 1 pi. Okay. So it consists of only sine function. The series in the terms are sine functions. Okay, and the n becomes to only the odd numbers. So we have that. Okay, and yes, please.
Why is there this k?
Yeah, okay, because cosine function, the value of cosine n pi depends on if n is even, then cosine, for example, cosine 0 pi, cosine 2 pi, cosine 4 pi, they are equal to 1.
Yeah.
So 1 minus 1 is 0.
Yeah.
And when n is odd, then the value is minus 1.
So you're trying to say like with n equals 2k?
Yeah. When n, because we are evaluated all the n here, because Bn n should be greater than or equal to 1. So they are all natural numbers. Yeah, and there are 2 cases for even natural numbers and for odd natural numbers. And for even natural numbers, we know the difference is 0. But when n is an odd natural number, then the difference is 2. Yeah. Just go to the detail. Yeah, because we want to simplify this associated trigonometric Fourier series.
And there, then you use k because.
Yeah, because that, as we know, because we know in general, right? This one x. Okay.
A n is
Yeah.
0.
A0 is 0 already, right? Yeah, and all the AN are zeros. So you can just eliminate them, right? And so now we have Bn and sin n x, right? Now, there are two cases for Bn. Yeah, when n is an even number, Bn is 0. Okay, so they can be just neglected, right? And when n is odd, so for n equal to 2k minus 1, because 2k minus 1 is an expression for odd natural numbers. Yeah. And then we go to here. Yeah. Yeah, to apply this result. Yeah. Sorry, that's a little bit quick. Thank you. Yeah, to slow me down. Good. Yeah, don't hesitate to do so. Okay. Yeah, no problem. Okay. Other questions? Okay, good. So okay, so we have once we so our target would be a periodic function which is absolutely integrable over a period. Okay, so we study such kind of function, right? And the Clark function is one of the cases, all right? And you can see, actually, most of the practical situation, you will encounter a periodic function which is absolutely integrable over a period. Now, so now we construct an associated trigonometric Fourier series. So we have two problems, okay? We have a so-called convergence problem. The convergence problem is the question that does the trigonometric Fourier series, okay, generated by f, all right, converge, all right, at some point in an interval. Okay, so this is convergence problem. Okay, so of course it will be perfect if we know that for some point in this period, this Fourier series converge, and for other points, all right, the series does not converge. And that's perfect, right? So we know exactly where this Fourier series converge, and then the rest will diverge. So that is good. And the other will be the representation problem. Is that if the series does converge, okay? So if the series does converge, for example, we answer in the first question at a point x and minus pi to pi, okay? So the question is that its sum. Its sum means the value of the series, okay? Because converge, right? So the value it converges would usually call the sum of the series. So is sum this function value? Okay, so that is the so-called the representation problem. Okay. Any questions about this problem? Because we have answered the first question first. If the Fourier series, all right, does not converge at the point, then it has no sum, right? Okay. So, but if it do have a sum, means that the associated trigonometric Fourier series converge at a point. Then we'll ask whether the sum equal to f of x. If the answer is yes, then f of x, I mean at some particular point x, can be written as the trigonometric Fourier series. Okay, so. All right, and so to answer both problems, we need the Riemann-Lebesgue lemma. Okay, we need this lemma. The lemma itself is quite interesting. So I state the lemma here. Okay. Now it's A. So if a theorem is numbered by alphabetical order, that means a theorem which is supplemental, not appeared in the textbook. So I use this naming system to indicate the difference. Okay, so let I be an interval. All right, I be an interval, can be bounded or unbounded. Can be open or closed or half open so in the real line. So suppose I is a interval. The arbitrary interval, okay? So interval can be, for example, the examples like AB, okay, closed interval, open interval, half open, half closed, unbounded, okay, unbounded, okay, so a lot of and as well as the whole real line cell. So I can be any of these kind of intervals. All right, can be bounded or unbounded, can be closed or open, or half closed, half open. All right. So anyway, just arbitrary interval. Now assume that f is absolutely integrable, all right, over I. Namely, we integrate the absolute value of f of x over this interval. The value is finite, right? We assume that. So that is the very general condition. Then for each beta in R, okay, we have this very interesting result. If we multiply the function f of x by using a sinusoidal, all right, signal, all right, and let the frequency goes to infinity, okay? So this is the angular frequency, right? So the angular frequency into infinity. Okay, and the phase beta is fixed, just in arbitrary, okay? So beta is called a phase, as we know. So this is phase. So this is angular frequency, right? Okay, the alpha is the angular frequency of the sinusoidal signal. Beta is just a phase, right? So we fix the phase, but let the angular frequency goes to infinity. The result is that this integral, all right, over it goes to a 0. Intuition, very important, you see. For example, all right, suppose I just say, I have, for example, here. Okay, so here this is the interval here. So suppose maybe I have a finite interval AB. Okay, and this is f of x. Yeah. Okay. Now, when I multiply this, so it's clear this function is absolutely integrable, right? Because you see, it's upper bound, it has maximum value and minimum value. Now, if we multiply with the sinusoidal signal, what happens? Well, it's just like you think about that. You have an image, okay? So let me, okay. All right? Yeah. And when you, because sine is oscillation, right? So that this is becomes to, okay. All right? And so what is that? It's f of x times sine alpha x plus beta. Yeah. As alpha goes to infinity, because the frequency goes to infinity, so the oscillation is like you can see when alpha goes up, the oscillation, well, tremendous. And as you see, when we integrate over this one, it's just like in a local, when you look at a very local microscopic point of view, the f of x becomes to a constant, right? Becomes to a constant. And within that small interval, it's just like a sinusoidal function, right? But for a sinusoidal function, you see that the integral over sinusoidal over a period is equal to 0. So you can see this is plus minus plus minus. So the integral over here, this is plus minus plus minus plus minus plus minus. Okay, and they will cancel each other, right? So the integral from here, all right, to here is one period for the sinusoidal signal. Then the integral will approximately equal to 0. Right. And so they cancel. And the phenomenon becomes to very similar to like in a local view that we have, just like we have a sinusoidal signal. And when we integrate over, so the integration, just like an area in the shaded area, so they will cancel each other. so they become to 0. Okay. So Riemann-Lebesgue lemma actually is a theorem to describe this phenomenon. Okay. So it is very intuitive. Very intuitive. All right? So I hope you understand that, why this is true. Because you can draw a signal like that. So later on, if you take the communication system course, maybe in the junior or senior year, you will see that it's just like a modulation. Okay, so you see that the radio signal, when a person in a radio station speak, then the signal, all right, over the air, all right, they will go out of the transmitter, and the signal actually is multiplied with a sinusoidal signal with different frequency. So you can see, say FM 100 means that the frequency is 100 megahertz, and if you say FM 108 means that the frequency would be 108 megahertz. Now with different frequency, then the signal will separate. Okay, and so you have different channels like that. So that you can see this is called a modulated signal. And if alpha goes to infinity, means that the frequency goes infinity. Okay, goes infinity. In this case, then this integral goes to 0. Okay, so that is the Riemann-Lebesgue lemma. Right, that's the Riemann-Lebesgue lemma. Okay, all right, and I provide a proof in my lecture notes before the statement of this theorem. Okay, so I don't want to redo it in the classroom, but I ask you to read my lecture notes. Okay. Any questions? Yes, please. Hmm? I'm sorry, I can't. You mean this here? Up? Okay. Oh, thank you.
And this is like under the 4, like
4?
4, and then below the is there 2k minus 1, or is it?
Yeah, because it's m pi.
Ah, and pi.
Yeah.
I,
Yeah, it's m pi. Oh.
I think it should be like 2k minus 1.
2k minus 1x. Yeah, I think it's correct. Yeah, because it's angular frequency. Yeah, I'm sorry. Yeah. But thank you for the correction. Okay. So any question about the Riemann-Lebesgue lemma? Okay. So we will use the Riemann-Lebesgue lemma to answer the convergence problem. All right. So now the partial sum function partial sum function. Right, can be written because by the Euler's formulas, so we can actually comes to okay. So maybe I read here. Okay, I use T. Okay, maybe I use T. Good. Yeah, because X is here. All right, so A0 is this is evaluated by this integral. And AN is 1 over pi. And F of T and cosine nt, okay, dt times cosine on x plus 1 over pi F of t sine nt dt sine nx. Okay, is that okay? So it's just a substitution of the Euler formulas. So this is A0, AN, and BN here. Okay, now, so we can put everything into only one integral. So 1 over pi F of t 1/2 plus summation and equal to 1 to m cosine nt and cosine nx plus sine nt sine nx. Okay? So together and the dt. And by the sum form, so that by the sum formula, this is equal to cosine n x minus t. Okay. Because it's plus, so we have minus here. Okay, so now we can simplify. Okay, and cosine n x minus t dt. And we will denote this part as a function. Okay. But a translation of a function, d sub m of x minus t dt, and where d sub m of x is defined to be 1/2 plus summation m from 1 to m and cosine nx. Okay. Okay. So this one becomes to d sub m of x minus t, because the argument becomes x minus t instead of x. Right? So we define this one. Okay. And in high school, we know how to evaluate this sum. Okay? We know how to evaluate this sum. So this sum actually depends on, so this is sine m plus 1/2 x divided by 2 sine x divided by 2. All right, for all x not equal to 2k pi. All right, so k is any integers. But if x equal to 2k pi, so you have sine k pi, but sine k pi is 0. Okay, so that if okay, so for those for x is we have special value, because when x is 2k pi, this one is equal to 1, because it's an even multiple of pi. So the cosine value is equal to 1, and 1 over 1 you have m. Is that right? Yeah. So incorrect. It's m plus 1/2. Okay. Okay, I find a mistake, a typo error in my notes. Okay, so this is so if x equal to 2k pi. All right, and this one is called a Dirichlet kernel. Okay, it's called Dirichlet kernel here. So that's why we use D, okay, to name this function. Okay. All right, so the partial sum function becomes to, if you know convolution, okay, maybe I will say something about that later. Okay, so you have you can express that. All right, so you can see the partial sum function can be expressed as an integral, all right, of some integram. This integram is the original absolute integrable function f of t multiplied with the Dirichlet kernel here. Okay, right, and all right, and you can see this kernel is also a periodic function, right? So this kernel is also which is a periodic function. With a period to pi. Okay? So it's also a periodic function with period to pi here. Okay? So f of t is a periodic function with period to pi, and the Dirichlet kernel is also. Okay? Right. So right now, so so we integrate over. So even though if x is fixed, then when x is fixed, because for every x we have this integral, right? So the integral is evaluated over t. Right? So when x is fixed, then it becomes to a function of t, and it's still periodic. it is still a periodic function too. Okay. So fix x, then as a function of t, this function is also periodic. Right. So if we look at as a function like h of t with x as a parameter, then it's also a periodic function. Okay. All right. So the integrand is a multiple of two periodic functions of t with the same period, pi. All right, and the definite integral is over one period, right? From minus pi to pi. So you can see that the same. So we can evaluate. So the same, we can do it by a little bit shift. So we shift the period by x, right, to the right. They should have the same value, right? Because it's periodic function, so that so they are the same, okay? Because the integration is over one full period. Okay. So when we shift them, we just like okay. So if we do the integration for one period, we can shift the integration into other interval, but with only one period, right? So for example, from minus pi over 2 to 3 pi over 2. It's also one full period. And the integral will be the same. Okay? So so we have this one. And then with that, we can do change of variable. Okay. So by doing, we let u equal to x minus t. Okay. So let u, right? Then we find that this is equal to pi minus pi, and f of x minus u, and dm u du. Okay. By change of variable. Okay. So you see that, and from the previous one, you know that this is equal to so this vector is a property of, so this is called cyclic convolution. Okay. It's called so they are called cyclic convolution of f and dm. Okay. Okay, so the partial sum function can be expressed as a cyclic convolution of the original absolutely integrable function f of t and the Dirichlet kernel. Okay, the Dirichlet kernel. Any questions? So if no, then we take a 5 minutes break.挂的耳机拿走了，因为收音就把音受到影响。 Okay, much better. Okay. Yep. All right. So it really surprised me that you didn't know some of the triangular identities in high school. Yeah. So if this is the case, let me know. All right. Because I usually assume that you know his background. Okay. All right. Okay. So so now we are able to express partial sum function as a cyclic convolution of the periodic function f of t and the Dirichlet's kernel. Now we look at the Dirichlet kernel here. It is clear because cosine function is an even function, and the constant function can be regarded as even function, so that the sum is also an even function. So the Dirichlet kernel is also an even function. Okay. All right. So we can further simplify that. First of all, we divide the definite integral into two definite integral, all right, over two shorter period, shorter interval. Okay. Okay. So we just the original integration interval is from minus pi to pi, but we deliberated to separate one single definite integral into the sum of two definite integral over minus pi to 0. The other is 0 to pi. Okay. And then now the Dirichlet kernel is even, i.e. Minus u equals to d sub m u, okay, for all u, right? So we know this fact. We know this fact, right? All right, and so we can do that. This is equal to here. Plus okay, and for our purpose, I change the dumping variable from u to v here. Okay, and now we can do we let u equal to minus v, right? We do the change of variable. When we do so, then the interval becomes from 0 to pi. Of course, you have to flip, right? But okay, so now you can change this integral to this integral, and the integration interval becomes from 0 to pi. Okay, become from 0 to pi. I hope you know how to do that. All right, just change your variable. Okay. All right, and okay, and so we combine them together. So we have 2 to pi, 0 to pi, And we have f of x plus u plus f of x minus u divided by 2. All right, so we divide by 2, so we multiply 2 here. All right, and the d m u d. Okay, so we further simplify, all right, the integral into this one. Okay. Now, okay, all right, and the Dirichlet kernel is equal to this formula when x is not equal to this discrete point, x not equal to 2k pi here. All right, and so under the integration sign, we can now t plus f of x minus t divided by 2. Okay, and the sine function m plus 1 over 2 t, and thus 2 sine of t divided by 2, and dt. Okay. Okay. Because we ignore the endpoint. Okay, so the integration, right? You see that we let t over when t greater than 0 but less than pi. In this range, you can see the Dirichlet kernel is equal to this formula. Okay, because it's equal to this formula. Okay. It's okay because the endpoint is not important. Okay, for dt, for this integrator. Okay. Okay. Now the limit, the partial sum function exists for some x in one period. If and only if, all right, if only if the limit m goes to infinity of this interval from 0 to pi, and f of x plus t plus f of x minus t divided by 2, okay, and the sine m plus 1/2 of t, 2 times sine t divided by 2, and the dt exists for some x in. Okay, so the convergence problem becomes to the question about the convergence of this integral. Now, as I said before, okay, we want to apply Riemann-Lebesgue lemma, right? But Riemann-Lebesgue lemma is a function, all right, times something here. Okay. Now, but as you can see here, we have denominator, which is a function a sinusoidal function, right? Okay, so so we have to do some replacement. Right? All right, and we will see, we will check. So we will check that. So that so this is not a very, but one thing is very, as we know, the sine function. The sine function, we know the sine theta will approximately equal to theta when theta is very small, right? We know this approximation. Okay, when they are very, very small. Okay, you can see, maybe I use absolute value here. When they are very small here. So you see the trouble point is because when t goes to 0, this denominator becomes to 0. Okay, and but the behavior of the sine function is equal to this one. So it will be. So we will see that the denominator actually can be replaced by 2. Means that because the singularity is when t is small, it is approached to 0, right? So and the denominator is very close to t when t is small. Okay, so now we want to show but we have to justify that, right? When we say that the limiter, if this limiter exists, the limiter is equal to this limiter, okay? So what we want to know, so we have to check. Okay, so to check this, we compute. All right, so what we compute the difference, okay? So we compute the limit m goes to infinity, okay, pi 1 over t minus 1 over 2 sine d divided by 2 and the fx plus t plus fx minus t divided by 2 and the sine m plus 1/2 t and dt. Okay? Right. So so this is the difference of these two integrals. Okay. And we want to show that the limit is equal to 0. Okay. Let me do it. Okay? No. Okay, so which compute this limit. And even though this function, okay, explode as t goes to 0, and also this function explode as t goes to 0, but their difference is